To ML with AP. This is the part 2 of the logistic regression video where we are trying to explain logistic regression, the intuition, maths, and we'll try to code it from scratch. In part 1 of this video, if you have not watched, I highly recommend you to go ahead and watch this, because this video will make much more sense if you have watched the previous one. In the first video, we have dealt with the intuition behind logistic regression. We have also discussed that why it is called a regression when obviously it is a classification. We have seen the maths behind it. We have also seen the maths behind the gradient descent optimization applied on logistic regression. Now we are going to discuss two important things in this particular video. The first being why logistic regression is considered as a base form or the basic form of neural network or perceptron. And the second, we are going to code our logistic regression on a stochastic gradient descent right from scratch. We'll not use the packages like SKLearn. We'll do it from scratch using basic packages like NumPy and Pandas. So let's stick around and start. So the first thing first, why logistic regression is considered as a simple neural network. Now towards my left side of the screen, if you see, this is what we have discussed in the part 1 of this video series. We had this, and just to a quick recap, we had on the left side over here, if you see, this is what we were trying to fit a straight line through our categorical output data, right? So we had this pass or fail, which was 0 and 1, and we are trying to fit, and we encountered some problem that, okay, my line extends from positive infinity to negative infinity, and it is not doing a good job of predicting the categorical data. So what we are trying to do, because since we are trying to predict the probability and it is squished between 0 and 1, let's squish or transform this line, this red line, into a S-shaped sigmoid function. That's what we did, right? So this is the basic of logistic regression. What we are trying to do, we had some parameter like x, which is the x-axis number of our study, and we were trying to predict whether the person is pass or fail. It was a binary classification use case. Okay, this is our logistic regression. Over here, if you see, this is a very simple artificial neural network. So we have bunch of x1, x2, x3. These are the inputs. Okay, we have the weights w1, w2, wm. What we are trying to do over here is we are trying to do the sum of this and put a bias or an intercept term. Over here we are calling it intercept. Over here we will call it bias term. So what it is doing? It is doing w1 x1, w2 x2, and so on and so forth till wm xm, and we are putting a plus b as a bias term. After that, what we are passing it through? We are passing it through a non-linear function. In this case, non-linear function is our logistic function or sigmoid function, which is represented as 1 by 1 plus e to the power minus z, right? So again, to recall, in a very simple perceptron, multi-layer perceptron or single layer perceptron based network, what we are doing? We are w1, x1, w2, we are summing it, we are passing it through a non-linearity, which is a sigmoid function, and it is giving you output. The output is, since it is passing through a sigmoid, the output we know that will be squished between 0 and 1, right? Because anything passes through sigmoid will be squished between 0 and 1. We already know that. Now, do you see the similarity between this? Over here, if you think it just as, let's say we have two variables over here. What will be my equation? My equation will be m1 x1 plus m2 x2 plus c, right? And instead of a line, it will become a hyperplane, right? That's all it is going to change. If suppose we have number of our study and one more feature, something like what else makes a person fail or pass, right? The number of assignments he has done, let's say. Okay, so if we have two variables or two features, number of study, which is x1, and number of assignments he or she has submitted, x2. What will be my equation of, instead of line, it will become a plane, and the equation of plane will be m1 x1 plus m2 x2 plus c. C will still be the intercept term, and then I'm passing it the same function through a sigmoid, and I'm giving it a probability, and I'm fetching the probability on the y-axis, right? Over here, if you recall, if there is just x1, x2, It is exactly the same thing which we are doing. We are doing W1 X1 instead of M1 X1. We are doing W1 X1, W2 X2, similarly to M2 X2, the second variable, second feature. And we are adding an intercept term B over here. We are adding an intercept term C. It's still a constant. It's just a bias. Here we call intercept, here we call it bias. And what we are doing, we are passing, in the logistic regression case, we are passing it through a sigmoid function over here, right? Squishing the line to give the probability. Here also, we are passing it through a non-linearity, in this particular case, logistics or sigmoid function. And we are getting the output. So, friends, what I'm trying to tell, a very simple perceptron or artificial neural network is exactly same as your logistic regression for a binary classification problem. It's exactly the same. There is no difference. And that's why, my friends, logistic regression is considered or can be considered as an artificial neural network, as a very basic artificial neural network, right? Okay, I hope, friends, this particular concept is well understood, because not many people talk, or not many people will make you understand it like this or visualize it like this, right? So I hope this particular concept is clear, right? In case you have any doubt in this, I would love that if you comment down, and I will try to answer. Maybe I will contact you and I'll try to have a one-on-one with you and try to answer you, okay? Now, with that being said, let's go to the last part of our problem, or last part of this series. Let's code from scratch. So as I promised that we'll code our logistic regression using stochastic gradient descent optimization without using any packages. And we'll do it with only a standard package like NumPy and Panda. Okay, this is our Jupyter notebook. So what we are going to do, we are going to implement logistic regression from scratch with SGD without using SKLearn, right? We are importing our standard packages, Pandas and NumPy. The only reason why I'm using SKLearn over here, and I said I will not, is because I'm loading the data set which is available. So I'm not using it for model.fit or anything like that, or creating the model. I'm only using it for getting the data set, okay? So I got the data set, and if you see, there are a lot of features over here, okay, and a lot of observations. So 13 columns, 178 rows. Now I wanted to keep things simple. So what I will do is I will do a little bit of filtering. So I get only one feature and one output, okay? So the feature which I'm going to select is like, if I get the feature names, so, and this is a multi-class problem. So I'll only take one class of there, okay? What I'm going to get is something is called flavonoids. It is one of the features, doesn't matter what it is. What I'm trying to get is only, I will retain one feature and one output variable, so that my things are become very simple, okay? So here is my data frame. I've done a little bit of filtering over here, and my data frame over here, it's one feature. This is my one X, okay, which is represented in column 1, and column 0 is my output variable. Okay, so let me just see. Okay, I put it in X and Y. I will show you my X. My X is bunch of numbers over here. Okay, my type of X is ND array, NumPy ND array, n dimensional array, X dot shape, so 130. So it's a vector, column vector with 130 rows. Okay. Now my Y is similar over here. Y, if you see, there are 0 and 1 predictions. So this is my predictive value. Now let's code our logistic regression on my X and Y. So one feature variable, one output. Very simple. Okay. What I'm trying to get is, I'm trying to get my len of Y. How many? It is 130 or something. Yeah, 130. And I'm initializing my M and C. M and C are my straight line. My intercept, C is the intercept, and M is the slope. Okay, I'm defining a learning rate also for my gradient descent. This is 0.01. Okay, I'm defining epochs. Epochs are nothing but how many passes on the data, on the 130 odd data it is going to take. So I'm going to take 100 pass, how many iterations during the SGD it will take. One of the metric for performance is accuracy for categorical or classification data. Right. In case of linear regression, it was mean square error. Over here, I'm seeing that how many predictions are getting right. That is accuracy. Okay. I have defined a small function which is sigmoid. It is self-explanatory. You can see that I'm passing z, and what I'm getting a sigmoid function which is 1 plus e to the power minus z. Right. Very simple. Now let's try to perform gradient descent. Okay. So what I'm doing is I'm running a first for loop over here for epoch, and epoch is 100 over here. I'm doing 100 time iteration over my data, and range in 1 and epoch, so it will take 1, 2 till 100th, right? And what I'm trying to do, since it is a stochastic gradient descent, I'm iterating on each of these data individually also, right? So for I in range len x is 130 or so. I'm trying to pick one data in the first epoch. And what I'm trying to do, I'm trying to compute the gradient. Now, if you recall in my last video, we have already gotten the gradient. What is the gradient? This is my hypothesis, right? This was my z, or the predicted value, mx I plus I. And this is my ith observed value. So I'm subtracting it, I'm passing it through a sigmoid function, and then I'm multiplying it with my xi, right? In case of intercept, my xi becomes 1, right? So if you see over here, in case of my intercept term or the bias term, it is only, there is no xi because xi is 1 for that, right? And then what I'm doing, my learning rate is there, simple gradient descent, okay? But I'm doing a stochastic. Why stochastic? Because I'm doing it for each of these observations or each of these row items, okay? As you can see over here. My learning rate, how I'm updating? M, my initialized value, minus learning rate into the gradient. And I'm taking a small steps downhill, right? Very simple. This is nothing great, right? These are the two lines which implements, these are the two lines which implements your stochastic gradient descent. That's it. So once my epoch has run, right, all the epochs have run, the M and C values, my intercept and this value that come. Okay. What I'm trying to do over here, anything, now I have to do the prediction. I got my straight line over here, right? And that's why it is called regression. I got my M and C values, but M and C values is not enough. I need to see how accurate my predictions were. What I'm trying to do, I'm setting a threshold of 0.5. With this being, and if I pass it through sigmoid function, my straight line, and the value which comes, if that value is greater than 0.5, predict it as 1, pass. If the value is less than 0.5, predict it as fail, 0, right? That's all I'm doing. Here, using this M and C, I'm doing my predictions, okay? And I'm doing my predictions on what? On the same variable, on the same observations which we have already seen. What I'm doing? Here, I'm just doing a calculation of the accuracy. How I'm doing the calculation of accuracy? Very simple, right? I'm trying to see that if my prediction is 0, and I'm trying to match it, that if my observed value is also 0, then my accuracy is increasing. If my prediction is 1, and it is matching with my observed value, my accuracy is going by 1. My counter is going by 1, right? Accuracy counter. If they are mismatched, if it either is 0 or 1 or 1 or 0, it is not matching. That what I predicted didn't match with my observed. That's my prediction will not increase. It's a counter. And then I'm dividing it by n, that counter, accuracy counter, dividing by n to get the accuracy. Very simple logic. Okay, let's run this. So M and C values, my slope and intercept came like this. My accuracy is 0.8, almost 80%. So 80% of the time I'm accurate. Okay. Now let's see. I'm trying to validate what I have coded using SKLearn also. So I'm using a standard SKLearn logistic regression module. Okay. And I'm doing a model.predict, model.fit and model.predict, right? Okay. And I'm trying to see the accuracy parameter for that also. The accuracy parameter came as 81%. Very similar, 80%, 80.76 and 81.53. Very similar prediction. Okay. Maybe the only difference is that they are using a different solver. Okay, that could be one of the difference, right? And I'm using a very plain vanilla stochastic gradient descent, right? So now we can output the prediction over here for the SKLearn. Model coefficient parameters also we can do. SKLearn also gives you the prediction probabilities, right? For each of the individual reported predictions, what was the class 1 and class 0 probabilities, right? Nothing great. Now what I'm trying to do over here is I'm trying to see that wherever I'm trying to predict all the three, what was the original prediction, what I predicted, and what SKLearn predicted. Okay, and I'm trying to make a new column also whether they were matched or not matched, right? My predictions did match with the SKLearn prediction or didn't match with the SKLearn prediction, right? So if you see over here, actually it was 0. I predicted it as 1 with my code. SKLearn also predicted it as 1, right? It is matched because this column is getting matched with our prediction and SKLearn prediction, right? So if you see over here, there is one scenario where our code predicted 1, SKLearn predicted 0, and the true value or the observed value was also 0. And that's why the SKLearn, I think, accuracy is a little higher, right? So you can see that. Okay. With that being said, I think we have come to end of this particular video, 2-part series. If you like these type of content, I have one request for you. Please do like, comment, subscribe, and share it with your friends. It will mean a lot to me. It will motivate me to create such video contents. Okay. With that being said, I will close this up and have a good day.